and something here we will need to integrate, right? We will need to integrate over Dex. We'll integrate this, the pressure, integrate the pressure to get the forces, okay? Any question about that? Okay. So let's go back to our MATLAB code to write these two equations. So I get the pressure. So this pressure I will multiply by sine theta panel, this panel, in negative to get the fx, and the fy is the same but with cosine, correct? We got fx and fy, and if we need to integrate, so the simplest way to do it is to define here 0, and each time just add fx to the old fx, and the same for fy, right? So at the end here, after this loop, we got the pressure at each panel, we got the fx and fy contribution at each panel. I'll keep adding. So at the end, fx and fy just numbers, and the total fx and total fy forces, right? How to get the lift out of these? But let's go back to our thing. So now I have, this is my u infinity, this is alpha, I have fx and fy. The lift is defined perpendicular to the free stream. So this is alpha. So my lift is fy cosine minus fx sine. Okay? So I'll go and do this. So the total lift is fy times cosine alpha, alpha of this time step, right? Minus fx times sine alpha this time step. And of course we like to keep track of the lift. So I will give it an index here at each k. Okay? And if you want the lift coefficient, so I'll just normalize this by rho u squared times b. Okay, so let's see if we do have any errors or something. No, that's good. Let's try to plot. I mean, we did not finish yet because we did not touch the wave, okay? So it's as if this is what solution is akin to what? Is close to what?
Steady.
Yeah, was a steady solution, right? So we didn't do anything in the wave. So let's plot T and CL and see if it looks nicely or not. Well, yeah, because you're working with 2 panels only. Let's make this 40, run it again. So yeah, it's sine. You're giving sine, at least you're getting, you know, it's just of much larger amplitude. We don't know why. We'll see if this is has to do with the wake or not. Hopefully we did not do a mistake. We'll see. Anyway. Because it's 10 and negative 10, or, right? 15, negative 15, this is the CL. It's very large. There is something here that we need to take care of. Maybe we have time, so you can. Okay. What is the unsteady Bernoulli equation? It's rho partial T, right? So rho u gamma divided by d and rho times summation all gammas minus summation all gamma over. Okay, hopefully. We'll see. Let's see what will happen if we adjust this. Anyway, if we couldn't get the correct CL, I will correct it on my own and send you the lines where we missed the sign or something. Okay. So we'll keep adding. So we're done with the loads.
Sorry, I didn't get how is gamma all being updated.
Gamma old,
Yeah. Like, is it being updated?
so at each time step, you have gamma old is equal to gamma, the new gammas that you just,
Okay.
right?
Okay. Yeah.
So let's do the wake, because this is the interesting part, and this is the, it's not easy, it's not obvious. The wake convection. First of all, there are obvious things. So first of all, the number of wake will be number of wake plus 1, right? We added the wake 1. And can you tell me what is the first wake element? So I will add something here, and I will append it by the gamma wake. So whatever you have an array for gamma wake, you will add a new value to it, right? The value of the newly shaped vortex. What is the value of the newly shaped vortex? Put it here. What's that?
All the other the bound ones you said.
Yeah, the last one of the bound, right? The last one of the bound at the trailing edge that we are shaping. So this is G bound of n plus 1, right? The last one of the bound. And the same for xy. So actually xy wake will be xy bound of n plus 1 and anything. Underneath, we will have the xy wake from before. Okay, each time I adding 1 and I'm adding the value of the wake vortex. So after this line, 78, the trailing edge vortex no longer belongs to the bound, but now it's a wake element. Okay, so I'm adding it to the gamma wake, and I'm adding xy to the xy wake. Okay. That's okay, but again, up to this point, the wake did not move. I'm just preparing it, my code. But I did not move the wake. The wake has to convect by the local velocity. So at each wake point, I have to go and compute the local velocity and move its xy by it. Okay? So if I'm gonna do it for each wake, so obviously I will do for I equals 1 up to what? N wake, right? I'm doing it for each wake vortex. Okay. What are the contributions of the motion of each wake vortex? I have a wake vortex. What are the contribution for this guy to move? What are the sources of velocity? What moves it? Why it moves? Well, we have bound vortices affecting it, right? So I have effect from bound vortices. What else?
The U.
The motion of the airfoil, because we're computing the relative velocity. So the motion. And what else? The other wake vortices, right? So bound, wake, and the other wake vortices. So bound and wake and the motion. Let's compute the motion. The motion is easy. So first, due to airfoil motion. So we will get the airfoil motion, which we already have here, something like this, right? Here it is. This is the velocity, but I want it not at a control point, I want it at the xy wake. So all what I need to do is just do this wake, right? So this is the velocity. I don't want the normal. There is no normal here. I just need the total velocity. Well, here is the total velocity. So xy wake, I will call this new, is xy wake. So this is the velocity of the airfoil. If this guy is not moving at all, if the wake is just stationary, what will be my velocity relative to the airfoil? So if this guy is moving with v and I'm stationary, what's my velocity relative to it?
0.
Zero is stationary, is inertially. I'm just stationary here, inertially with the inertial frame, right? This guy is moving v like this.
Oh, then it's V.
What is my relative velocity with respect to it? It's the negative of v,
Negative.
right? So the negative of this, here is the negative of this v motion times what? So we're updating position. Velocity times what?
dt.
dt. Very good. So you got this part. the second part, we said this is due to F1 motion, then due to, you said bound vortices, right? So due to bound vortices, what should I do? Pi sub r. For each bound vortex on this point, right? Each means for loop, right? J equals 1 up to what? Bound vortices up to what?
N, right?
N, very good. Okay, for each one, I will do the bias of R exactly. The bias of R. The bias of R takes two things. X, Y of the point. What's the point here? The wake point. Very good. So X, Y wake of this guy. And what is the vortex location? What's the vortex location?
Each bound one.
X, Y bound. Very good. Of J. What is this result? It's the total velocity which I need. But assuming unit gamma. My gamma at this panel is not unit. And I determined its value, so I'm going to multiply by
Strength.
gamma bound of what was your index? J, very good. This is the total velocity. As you said, I'm going to multiply by delta t, and I will update my position the same way. So xy nu is equal to, actually xy nu, right? So I'm going to keep adding it, plus this guy. And we're done here. And the last one is very similar, is due to what? We did F1 motion, did bound vortices, what's the last one? Wake vortices. So this is easy. This will be changed to what?
W and W.
In wake. And here, this is wake. And this is wake, right? And that's it. So we need, of course, to say that xy wake for the next time step is actually the new one, right? And hopefully this is okay. This is done. Let's see what we will get. Let's see. So, okay, this one end is missing. This is easy. So we have for loop. Oh, we did not close this, right? Okay. Yeah, it's gonna take time. A very long time, but yeah, as you see here, it's taking a little time. If you do it in Fortran, it's just a fraction of a second, and we get nothing out of that. So let's see. Why we're getting nothing? Let's see. Oh, NAND. Very good. That's good to know. So that's good to know. Can you tell me why we might be getting NANDs?
Are we like not satisfying like the number of rows and columns of the matrix or something?
Might be. What is a more compelling reason? Let's see. When we look at anything, so maybe here. So here is the start of the time simulation. Here we're getting the effect of all wave vortices on the bound, right? That's okay. But then here, we're getting the effect of the bound vortices on the wake. That's also okay. Here, the effect of wake vortices on the wake, right? Effect of wake vortices on the wake. So I have a wake vortex, and I have a bunch of other vortices. I'm getting the effect of each wake vortex, including this one on itself. What's the distance between this one and itself? 0. So if you go to your bias of R, if you have R equals 0, is dividing by 0 here. Yes, but dy and dx is 0, that's fine. So MATLAB will have 0 plus 0. This is NAND, this is not a number, right? So this might be the source. This is why we need to have a cutoff here. So some distance below which, if the two vortices come very close to each other, it's as if they don't affect each other, okay? It's as if you're putting a core for your vortex. It's not very ideal implicit vortex. So we're getting a cutoff so that if this R is less than the cutoff, then your induced velocity is what is inside the core. It's not the gamma over 2 pi r anymore. I mean, the simplest solution is to put them as zeros. The other more realistic solution is to put a different equation. Instead of gamma over 2 pi r, instead of 1 over r distribution, it's linear distribution. So something like, so this is r, and this is the tangential velocity, it's gamma over 2 pi r, so it's like here. So at 0 r it goes to infinity. We need to shop this at some cutoff. This is our cutoff, right? It's up to you. What do you do here? Maybe either 0, or the best thing is to do it linearly in r, okay? If you want to do it, we'll do it 0 here. It's easy. And the cutoff typically is 10 to the power negative 5 from the chord. Our chord is 1. And we make the cutoff on r square, so this is a square. Let's save this and see what happens. So, UVLM class, let's go here, takes some time. Do you have any question, please?
Sure. Would it be possible if you don't have the cutoff, but like in the last part
yeah,
if you're updating, we don't just calculate the wake effect of
Yes,
that critical?
you can do that. So we get a nicer shape. Still, there's a problem with the code, but at least no nans anymore. You're right. We can do this here. So what we're doing here, what we are doing. So we're getting the effect of the j wake vortex j on the I wake vortex. You can say simply here that if j equals I, just ignore it, whatever. Okay. Yeah. But this is general, just to clear this headache, because one of the problems that we encounter when we do flight. So if you do an airplane stuff, so here's the wing is doing pitching, plunging, and there is a huge flow coming. So the flow really takes care of all the vortices behind. But the issue with flapping is that the insect or the bird wing goes like this, so create some wake here, the wake is stationary, and come back. So it needs its wake again, right? This does not happen for an airplane. So this is something called wake capture. We'll talk about it next time when we talk about flapping flight. But now, here we were afraid that effective wake, we were afraid that two wake vortices come very close to each other. So we can take care of that here. But now, it might be also a wake vortex coming very close to control point, to the wing. So you can get all sorts of things